In this episode, we start looking at the practical ways organizations protect data, even when that data has to be stored, processed, searched, shared, or moved between systems. When you hear terms like masking, hashing, filtering, tokenization, encryption, de-identification, transposition, and obfuscation, they can sound like different names for the same basic idea. They are related, but they do not all solve the same problem. Some methods hide data from casual view. Some transform data so it cannot easily be reversed. Some replace sensitive values with safer substitutes, and some control whether data is allowed to leave a system at all. As you build your security plus understanding, you want to listen for the purpose behind each method. The question is not just whether data is protected. The better question is how it is protected, who can recover it, and what risk remains if someone gets access to the protected version. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. Data protection begins with knowing that data can be exposed in more than one way. It can be exposed when it is stored in a database, copied into a report, transmitted across a network, displayed on a screen, exported to a spreadsheet, used by an application, or shared with a partner. One control rarely solves every version of that problem. A system might encrypt a database at rest, mask account numbers on a customer service screen, filter sensitive fields from logs, and tokenize payment card numbers before storing them. Each method reduces a different kind of risk. Encryption protects data by making it unreadable without the right key. Masking protects data by limiting what a person can see. Filtering protects data by preventing certain information from being included or sent. Tokenization protects data by replacing the real value with a substitute. These differences matter because exam questions often describe a situation and ask which method best matches the goal. Masking is one of the easiest methods to picture because you have probably seen it in everyday life. A receipt may show only the last 4 digits of a payment card. A customer service portal may show part of an email address, but hide the rest. A benefits website may display only the last few digits of a social security number, so the user can confirm the record without seeing the full value. Masking does not always change the original data in the underlying system. Often, the real value still exists in the database, but the application displays only a limited version to the person viewing it. That makes masking useful when people need enough information to recognize a record, but do not need the full sensitive value. The risk is that masking can give a false sense of safety if the original data remains accessible somewhere else. You should think of masking as a display control, not as complete data destruction. Hashing works very differently from masking because hashing is designed to create a fixed output from an input value. A hashing process takes data, runs it through a mathematical function, and produces a hash value. A strong hash function is one way, meaning you should not be able to take the hash and turn it back into the original value. This makes hashing useful for integrity checks and password storage. When a password is stored properly, the system should not keep the actual password in readable form. Instead, it stores a hash of the password, often with an added random value called a salt to make attacks harder. Later, when you type your password, the system hashes what you entered and compares the result to the stored hash. If they match, the system can authenticate you without needing to know the original password. Hashing is not encryption because there is no normal decryption step. Filtering is about controlling what data is allowed to pass, appear, or be retained. You can think of filtering as a decision point that removes, blocks, or limits data based on rules. For example, an organization may filter sensitive information out of application logs so passwords, access tokens, or account numbers do not get written into files that many administrators can read. An email gateway may filter outbound messages looking for regulated data before it leaves the company. A report may filter out certain fields before it is shared with a team that does not need them. Filtering can also be part of data loss prevention, DLP, where systems look for patterns that resemble sensitive data and then warn, block, quarantine, or alert on the transfer. Filtering is powerful, but it depends on good rules and good context. If the rules are too narrow, sensitive data may slip through. If they are too broad, normal work may be interrupted. Tokenization replaces sensitive data with a substitute value called a token. The token can look realistic, but it is not the real data. In many payment environments, tokenization allows an organization to store or process a token instead of storing the actual card number. The real value is kept in a separate protected system, sometimes called a token vault. When the business needs to complete an authorized transaction, the token can be mapped back to the real value by the trusted tokenization service. This reduces exposure because many systems never touch the original sensitive data. If an attacker steals a database full of tokens but cannot access the token vault or mapping service, the stolen data is much less useful. Tokenization is different from masking because it replaces the value, not just the way the value is displayed. It is also different from hashing because tokenization can be reversible by an authorized system. Encryption protects data by transforming readable information into unreadable ciphertext using cryptographic keys. Unlike hashing, encryption is designed to be reversible when the proper key is available. If you encrypt a file, database field, backup, or network session, the goal is that unauthorized people cannot understand the contents even if they get access to the encrypted data. Encryption can protect data at rest, which means data stored on a device, server, database, or backup. It can also protect data in transit, which means data moving across a network. The strength of encryption depends not only on the algorithm, but also on how keys are generated, stored, rotated, protected, and retired. Losing a key can mean losing access to the data. Exposing a key can mean exposing everything protected by that key. For Security Plus, remember that encryption is about confidentiality through controlled readability. Transposition is a form of data transformation where the position or order of characters is changed. It can be useful to understand as a simple historical or conceptual method, but you should not confuse it with strong modern encryption by itself. If a word, number, or message has its characters rearranged according to a pattern, someone who knows the pattern may be able to reverse the process. That is the basic idea behind transposition. The data has not necessarily been replaced, removed, or securely encrypted. It has been rearranged. In modern security discussions, transposition may appear as part of broader obfuscation or transformation concepts, but it should not be treated as a strong standalone control for protecting sensitive data. If an exam question describes rearranging characters or changing their position without using cryptographic keys, transposition is likely the concept being tested. It hides the original form, but it does not automatically provide strong confidentiality. Deidentification is used when an organization wants to reduce the chance that data can be tied back to a specific person. This matters in privacy, research, analytics, testing, and reporting. A hospital, for example, may want to study patient trends without exposing individual patient identities. A company may want to analyze customer behavior without giving analysts direct access to names, addresses, account numbers, or other identifying details. De-identification may remove direct identifiers, generalize certain values, mask fields, replace values, or separate identity data from activity data. The goal is to make the dataset less personally revealing. Personally identifiable information, PII, is often the kind of data people think about here, but the same idea can apply to other sensitive categories. De-identification is not always perfect. If enough indirect details remain, such as location, age, dates, and unusual events, someone may still be able to re-identify a person by combining clues. Obfuscation means making something harder to understand, analyze, or misuse. In data protection, obfuscation may involve altering values, changing names, hiding patterns, scrambling formats, or making information less obvious to someone who should not understand it. Developers may obfuscate code to make reverse engineering harder. Security teams may obfuscate sensitive values in logs so casual readers cannot see secrets. Training or test environments may use obfuscated production-like data so systems behave realistically without exposing real customer details. Obfuscation is useful, but it is not the same as strong encryption. It often slows people down or reduces accidental exposure, but a determined attacker may still recover meaning if the method is weak or predictable. That is why obfuscation is best understood as a risk reduction method. not a guarantee of secrecy. When you see the word obfuscation, think hidden, blurred, or made less understandable, rather than mathematically protected in the same way as encryption. These methods often work together because real systems have layered needs. Imagine a customer support system that stores sensitive customer records. The database may encrypt sensitive fields so stolen storage media does not reveal readable information. The application may mask certain values so support staff can verify identity without viewing the full record. Logs may filter out passwords, access tokens, and full account numbers before they are saved. Payment details may be tokenized so the company does not store full card numbers in its main customer database. Analytics data may be de-identified before being shared with a reporting team. Code or configuration details may be obfuscated before being distributed outside the development team. None of these controls is exactly the same, and none should be chosen just because it sounds secure. The right method depends on whether the organization needs to read the original data later, prove integrity, reduce exposure, or limit what people can see. A common misunderstanding is assuming that hidden data is always protected data. Masking a value on a screen does not mean the original value is gone. Obfuscating a file does not mean it is cryptographically secure. Hashing a value does not mean it can be decrypted later. Tokenizing a value does not mean the token itself has no risk if the mapping system is exposed. Encrypting a database does not mean every person with application access is blocked from seeing the data. Each method has a boundary. It protects against some risks and not others. This is why security work often asks you to be precise. If the risk is someone reading stolen backup files, encryption may be the answer. If the risk is a help desk worker seeing full account numbers, masking may be better. If the risk is passwords being recovered from a database, hashing with proper safeguards is the expected approach. Another helpful way to separate these ideas is to ask whether the original data can be recovered. Encryption is reversible if the correct key is available. Tokenization is reversible if the authorized mapping system is available. Masking may not change the original data at all because the full value may still exist behind the scenes. Hashing is normally not reversible because the purpose is to compare outputs without recovering the input. Filtering may remove data from a flow or output, which means the filtered copy no longer contains the removed information. Deidentification may or may not be reversible depending on how it is done and whether identifying data is kept separately. Obfuscation varies widely because some forms are easy to reverse and others are more complex. On the exam, this recoverability question can help you avoid traps. A scenario that needs later recovery usually does not want one-way hashing. A scenario that needs one-way verification often does. You also want to connect these methods to the data lifecycle. Data is not protected only at the moment it is stored. It must be protected when it is collected, entered, processed, displayed, transmitted, logged, copied, backed up, analyzed, archived, and eventually disposed of. Masking may matter most at display time. Filtering may matter when data is exported, logged, or transmitted. Encryption may matter during storage and transmission. Tokenization may matter when systems need to use a substitute instead of the real value. De-identification may matter when data leaves its original business purpose and enters reporting, research, testing, or training. Obfuscation may matter when information needs to be harder to interpret but still usable in some limited way. Security failures often happen when data moves from one context to another. A production database may be well protected, but an exported spreadsheet, copied log file, or test dataset may expose the same sensitive values. For exam-style thinking, focus on the wording of the scenario. If the question says the organization must prove that a file has not changed, hashing is probably involved because hashes are widely used for integrity. If the question says the organization must store passwords without being able to read them later, hashing is again the likely answer. If the question says only the last few digits should be visible to a representative, think masking. If the question says sensitive values should be replaced with substitute values while a secure system keeps the mapping, think tokenization. If the question says data must be unreadable without a key, think encryption. If the question says fields should be removed before reports, logs, or messages are shared, think filtering. If the question says identity should be removed from a dataset, think deidentification. If the question says information should be made harder to understand or reverse engineer, think obfuscation. The larger lesson is that data protection is not one control with one name. It is a set of choices based on how the data is used and what kind of exposure you are trying to reduce. Masking limits what someone sees. Hashing supports one-way verification and integrity checking. Filtering removes or blocks sensitive data from a particular output or flow. Tokenization replaces real values with controlled substitutes. Encryption makes data unreadable without the right key. Transposition rearranges data, usually without the strength of modern cryptography by itself. Deidentification reduces the link between data and a person. Obfuscation makes information harder to understand or analyze. When you can explain the difference in plain language, you are much better prepared for security plus questions and for real security conversations. You do not have to memorize these as isolated vocabulary words. You need to recognize the problem each method is meant to solve and the protection it does not provide.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.